So welcome again. In this recording, I will be implementing the Prüfer Codes algorithm. So how we can transform a graph or a tree into a Prüfer code, and how we can reconstitute the representation of a tree from a Prüfer code. So for this, I will remind you about the Prüfer code. So I have a tree, and so a tree, it's a graph that does not have a cycle, and I need to find its Prüfer code. So for the vertices, it should have labeling, so it's either numbers or characters, but they should be ordered, so I can find a way to order them. So for example, in this example, I have numbers, so they have order from 1 to 8. So I have here 8 vertices, and the Prüfer code, will see that it will consist of just 6. So it's always the number of vertices minus 2. So I need to pick the leaves, so those with degree equal to 1. So in our implementation in a while, I need to find a way to represent leaves. So I need an array, or an adjacency list, or a vector. I don't know, we'll see. However, I need to pick always the lowest vertex in terms of numbering here or labeling. So I need to sort them to pick the minimum. So, and we already learned in the first tile that we can use a priority queue. So we have solved that in order to pick the smallest leaf. So I have here 1. So I would write 1, and next to it I will write 5, and then I will delete 1. So I also need to find a way to delete a vertex or an edge from the graph. So obviously we will not delete something, we will use a vector of booleans to say that this edge is in or is not in the graph. So now I have 2, 7, 3, and 6. So the smallest one is 2, and its adjacent vertex is equal to 5, and then I will delete this. Now I have 5, 7, 3, and 8. So obviously the smallest one is 3, and its adjacent vertex is 4. Now I have 7, 5, and 8, because 4 and 6, they are not leaves. So I will pick 5 because this is the smallest vertex, and its adjacent one is equal to 4. Now I have 7, 4, 6, and 8. The smallest one is 7, and next to it I should write 4. Now I have 4, 6, and 8. So the smallest one is 4, and its adjacent vertex is 8. So if I will do so I have here 5, 5, 4, 4, 6. So this is the Prüfer code. So this is the second column. So this is the Prüfer code, and this is the sister code. So as you can see, I have 1, 2, 3, 4, 5, 6. 6 digits. However, the number of vertices is equal to 8. So let's suppose now I have the Prüfer code, and I need to reconstitute the tree. So I will erase all these, and I will stay on the same slide in order to reconstitute this. So my Prüfer code is equal to 5, 5, 4, 4, 4, 6. So I know that the Prüfer code is constituted from 6 numbers, so it means that the tree is constituted from 8 vertex. So what I will do, that I will add 8, which means the number of the biggest vertex. It has the biggest labeling. So in our case is 8. For example, if I'm using a character, so I will count the number of characters, and I will pick the correct character, the convenient character. So what I will do, that in this extended Prüfer code, so I need to find the missing number. So I have now this set of numbering. So obviously I don't have 1 here, because if I should start from 1. So what I will say, that 1, and I will write delete 5. So delete means it's the edge. So I will delete the first one. Now I will consider this set with this value. So I will, as if I'm union 2 sets, the sets that remains from here and the one that is constituted now. So I will check which number is missing. So I have 1, but I don't have 2 in this set. So I would write 2, and the second one would delete the second number here. Now I have 1, 2, 4, 4, 4, 6, 8. So I don't have 3. So 3, delete the third number, 4. Now I have 1, 2, 3, 4. I don't have 5. So 5, delete 4. Next, I have 1, 2, 3, 4, 5, 6. I don't have 7. So 7, delete the upcoming number, 4. I will continue. I have 1, 2, 3. I don't have 4 now. 4, delete 6. So again, I'm looking on this set and the remaining set here. 1, 2, 3, 4, 5. I don't have 6. So 6, delete 8, and obviously I have finished. So those 1 will constitute the edges. So I have edge from 1 to 5. So this is my first edge. 2, 5. This is my second edge. 3, 4. This is the third edge. 5, 4. 7, 4. 4, 6. And 6, 8. So I have reconstituted the tree. So let's pick another example. So let's see. So this is the animation. So let's have this. So let's find the Prüfer code of this and then reconstitute it using the second algorithm. So I have to identify the leaves. So I have 10, 3, 5, 8, and 9. Other vertices, they are not leaves because their degree is not equal to 1. So I will pick the smallest vertex label. So here is equal to 3. So 3, next to it, I will write 7 and I will delete this one. Now I have the leaves. They are 10, 6, 5, and 8. So the smallest one is equal to 5 and the adjacent vertex is equal to 4. And now 4 is the smallest vertex. So I write 4, 9, and I will delete 4. So obviously here 9 is not a leaf because it has a degree of 3. So now I have 8, 6, and 10, sorry. So the smallest one is equal to 6 and its adjacent vertex is equal to 9. So still 9 is not the smallest vertex label. I have just here 8 and 10. So I write 8 because this is the smallest one, and next to it I have 2, and now 2 is the smallest vertex. So 2 next to it I will write 9 because this is the adjacent vertex, and now 9 is the smallest vertex because I have just 9 and 10 as leaves. So 9 next to it I should write 1. Now 1 is the smallest vertex and I should write 1, 7, and it ends here because at the end of the Prüfer code I should have just 2 vertices. Now that I have the Prüfer code, so this is the second column, 7, 4, 9, 9, 2, 9, 1, 7. So this is my Prüfer code. So in order to reconstitute the tree, I need to append the maximum number or maximum label of the vertex, which is equal to 10. So I have it here. So this is the extended Prüfer code. So I will erase everything and try to reconstitute the tree. So I will start. So in this set, I have 1, I have 2, but I don't have 3. So I will start 3, delete 7. Now I have 1, 2, 3, 4. I don't have 5. So 5, 4, because this is the second one and I will delete it. Next, 1, 2, 3. I don't have 4. 4, 9. Continue. 1, 2, 3, 4, 5. I don't have 6. So 6, 9. Again, I have 1, I have 2, I have 3, 4, 5, 6, 7. I don't have 8. So 8, 2. Next, 1. I don't have 2 anymore. So 2, 9. I will continue. I have 1, 2, 3, 4, 5, 6, 7. 7 is here. 8 is here. I don't have 9. So 9, 1. Now I don't have 1. So directly I have 1, 7. And then I have 1, 2, 3, 4, 5, 6. I don't have 7. So 7 and 10. So those are the edges. So let's see if it's correct. I have 3, 7. I have 5, 4. 4, 9. 6, 9. 8, 2. 2, 9. 9, 1. 1, 7. And 10, 7. And this is correct. So let's move to our Moodle and see how we'll implement these two algorithms. So they are asking us to implement the following functions in order to generate a Prüfer code from a tree. So we need to write two functions. The Prüfer code generator, so it calculates the degree, so they are telling us what to do. So first we need to calculate the degree of each vertex. So it's easy to do. I just need to loop over the adjacency list and to calculate the degree. So I just need to know the size of the adjacency list. So using a priority queue, okay, I will enqueue the nodes with degree 1. Yes, because those are the leaves. So the leaves, I will add them into a priority queue. I will loop v minus 2 times. So why I will loop v minus 2 times? Because I need to generate a Prüfer code of length v minus 2. So I just need to do the calculation v minus 2 times. At each iteration, I will remove one element from the priority queue. This is very obvious because I need to remove the smallest leaf, the leaf that has the smallest label, and make it out of the tree. So how can I make it out of the tree? I'll be using something like a Boolean vector in order to say that it's not part of the graph. Then I will loop over its neighbors and pick the vertex that is still in the tree, obviously. So I need to pick the, like in the animation or the example, so I need to pick the adjacent vertex, and the adjacent should be still in the tree, obviously. So how we know that it's still in the tree? Because we already make it out of the tree because of this Boolean vector. So we update the Prüfer code. So the Prüfer code is the output, so it's a vector of integers, and the degree of the neighbor. So the neighbor, it will decrease because I have deleted one of the edges, and then push the neighbor if it degree is now 1. So if the neighbor or the adjacent vertex is now a leaf, I should push it into the adjacency, the priority queue. So I need for the second function, which is print, so it needs to print the Prüfer code vector. So in a fancy way. Why in a fancy way? I don't know why Mr. Bean is here. So because I need to print the commas and the brackets also. So let's see what we have as a skeleton. So we have a vector of integer. We have the adjacency list, which is a vector of integers. We have v, the number of vertices. I have a vector of integers of Prüfer code. So the Prüfer code, it contains the vertices number. The reading function was given, sorry, and I need to write the Prüfer code function that generates the Prüfer code, and another one for the printing. So let's start with the Prüfer code generator. So they are telling us that I need to calculate the degree. So there's no variable for degree, so I just need that here. So let's start with the degrees. So a degree, it should be for each integer. So it should be a vector of integer. So vector of integer, I will call it a degree. And this, so the degree, so the number of element of this one, it should be equal to the adjacency list size. So I don't know here the size of the adjacency list, so let's calculate that. So let's say int n equal, so I will copy this so that I don't have some errors. So it's adjacency list dot size. So it tells us the number of vertices. So I can pick v, that's the same, but I will keep this one, so just to know that we can also get the number of vertices from the adjacency list. So let's loop over the adjacency list. So int I equal to 0, I less than n, I plus plus, and I need to calculate the degree. So degree of I, it should be equal to adjacency list of I dot size. So I know now the degree of each vertex. So at the same time, since I'm calculating the degree, I will push into the priority queue those vertices with degree equal to 1. So for that, so if degree of I is equal to 1, so it means it's a leaf, I will use a priority queue and I will push I. So leaves. So now I will declare a priority queue of variable. So the name of the variable is called leaf. So priority queue. So it's of type integer because it contains the vertices number, and it would be called leaves. So I would say here leaves dot push. So obviously I will not push I because we know that the priority queue, it will sort the numbers in descending order. So I will push minus I, and whenever I'm dealing with the priority queue, I will use the negation of I. So I have calculated the degree. I have pushed into the priority queue those vertices with degree equal to 1, so the leaves 1. So then I need to loop, as they told us, n minus 2 times or v minus 2 times, because I need to generate number of the Prüfer code is of length n minus 2 or v minus 2. So I have the Prüfer code here, so I just need to initialize it because we didn't say how many values there is in this code. So I would say resize n-2 or v-2, and then I need to loop n-2 times. So for int I equal to 0, I less than n-2 I plus plus, and I need to do the following. So obviously I need to pick the smallest code, so I need to pick the top element in the priority queue. So this is very easy. So int leaf, it would be equal to leaves dot top. So I got the top element, so obviously I need to pop it directly. So leaves dot pop in order to remove. So now I have this one, so I need to remove it from the graph. So what does it mean I need to remove it? So I will have a Boolean vector to say that it's in the graph or not in the graph. So I will call it killed. So killed minus leaf, because leaf it's the negation, is equal to true. So for that I will have a Boolean vector. So it's a vector of bool. So it's called killed. So it has an element and all initialized to false. So a vector called killed, it contains an element and all initialized to false. So they are as if at the beginning they are all in the graph, and whenever I am picking the smallest vertex label, I'm removing it from the graph. So once it is removed, I need to find its adjacent vertex that is still in the tree. So I need to loop over its adjacency list and pick the one that it's still in the tree. So it means that it's killed, it's still true. So it's not yet killed. And then I need to check its degree, and then maybe I will push it into the priority queue. So let's do that. So first I need to loop over the adjacent vertex of this leaf and pick the one that is not killed. So obviously I need to loop over, so I need an iterator. So there's a lot of ways, so I will use an iterator here. So for int u in the adjacency list of the not leaf, so adjacency list of not leaf. So what I will do that, I will check if there's one not killed. So if not killed of u, so it means that I have a neighbor. So obviously there's just one. There's not multiple one because we are in a tree. So obviously there's just one here. So I have v equal to u, and I can do a break because there's no need to continue. In all cases, there's no way that we can find two vertex. So if I want to be more precise, I should write break, and it would be more convenient because I can just find one vertex. So once this v, so this adjacent vertex is found, so okay, this is the Prüfer code. So here I should write a Prüfer code. For example, I have I, because this is in order, because I have a loop here, it should be equal to v. And if I will the degree of v, now I should decrement the degree of v, and if it's equal to 1, so it's leaf, now I can push it again into the priority queue. So I can decrement, so I will write it first. So degree of v minus minus. So and then I would say if degree of v is equal to 1, I will push. So I should say leaves dot push of minus v. So what I will do here is that, for example, here this is a post incrementation. Since it's on one line, I can do a pre-incrementation, and also I can, since it's a pre-incrementation, I can write it directly here into one instruction. So this means since it's a pre-incrementation, so first I will decrement the degree of a v, and then I will check if it's equal to 1, and if it's the case, I would push it into the priority queue. So this is the code for the Prüfer code generator. So let me repeat it quickly. So first I had to calculate the degree of each vertex. So this is very easy. I just need to find the size of the adjacency list of that vertex, and if the degree of that vertex is equal to 1, I will push it into a priority queue. So I'm using minus here because we know that priority queue sorts the numbers into a descending order. So I have a priority queue of integers for that. Then I have resized the Prüfer code because it's equal, the Prüfer code size is equal to the number of vertices minus 2. And then I have looped n minus 2 times. For the same reason, I have picked the smallest vertex from the priority queue, and I have made it as out of the tree. So I have used a Boolean vector kill. At first, all initialized to false, and at each time I have picked a vertex, I am making it out of the tree. Then I have looped over its adjacent vertices, and I have picked the one that is not killed. So if it's not killed, the u1, so this is the iterator, I'm saving the vertex number in v, and this v would be part of the Prüfer code. So whenever I'm decrementing v, and if its degree is equal to 1, I'm pushing it into the priority queue. Now that I have my Prüfer code, so it's filled, it's here, so I just need to print it. So in order to print it, it's a bit fancy, so I need to print a bracket. So I just copy paste it here in order to know what I will do. So first I have to print an opening bracket, so there's no space after, and then I have comma 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 except the last one. So as if I should print 5 out of 6. So if v is the number of vertices, I need to print v minus 3 because the Prüfer code is v minus 2, and I need to keep this one because in the loop I need to print number and a comma. So for int I equal to 0, I less than v minus 3, I plus plus, I should print f percentage d comma space. So the first one is the Prüfer code. Prüfer, so I will copy it from here, of I. So in our case, I have printed till 6, comma, and space, and it remains the last one. So it remains 0 and closing brackets. So it's percentage d closing bracket. And here I have the Prüfer code of, for example, v minus 3, or the Prüfer code size minus 1. Also, I can have this, so Prüfer code dot size, so it's v minus 2 minus 1, or I can write v minus 3 directly. So I will remove this. So let's do a check and see if it's correct. So it works with all the examples. So let me repeat quickly the Prüfer code generator again. So we have calculated the degree of each vertex. We have pushed those with a degree equal to 1, so the leaves one, and then I have looped n minus 2 times. I have picked the smallest vertex. I have made it out of the tree. Then picked the sole vertex that is adjacent to that vertex. I have decremented its code. I have added as a Prüfer code, and then push it if its degree is equal to 1. So let's move to the last part, which is to generate the graph from a Prüfer code. So they are asking us to implement the following functions in order to generate the edges from a Prüfer code. So we need first to read. So fill the vector Prüfer code with the input. Input is the Prüfer code. So we have here the input, but they are not giving us the number of elements. So we will see here a trick. So it's already written on how to do that, and I will explain it in a while. So the Prüfer to edges, it calculates the edges of each vertex. So how can I do that? So again, I'll be using a priority queue. So I will enqueue the nodes with degree 1. For each vertex in the Prüfer code, pop one vertex from the queue and form the edge. So I'll be using a priority queue. So why I'll be using a priority queue? So in our case, so I don't know if it's written here, so it's not here. So I need to find a way to my priority queue. So it's called leaves. So I should calculate those leaves which are equal to 1. So we already know that. So I need to calculate the degrees for that. Then so add it twice in both directions so that your input matches with mine. So why I'm doing this? Because in order to validate the output, we have to consider both directions of the edges. So we decrement the vertex degree, and if it's equal to 1, we enqueue it in the queue. So don't forget at the end to add the last edges. So we'll see how we'll do that. So it's not very easy to, so there's no really hints here. So just ways to know what to do. So they are just giving us some hints, but not the full hints like in the previous exercise. And the print, so I need to print the edges. So again, so they are telling us don't forget to sort it beforehand because it needs to be sorted so that it matches my output. So for the reading, as you can see, there is no number of elements, so there's no for loops. So what I will do that in our code, I have used while in. So I'm reading an integer a. So as long as there's integers in the input, I'm pushing it into the proofer code. So as long as there's input, I'm pushing it into the proofer code. So in our case, this is our proofer code. So I need another function that generates the edges. So let's see what we have. I have a vector of integer, I have the proofer code, and I have a pair of integers with edges. So obviously an edge is a pair of integers, and I need to print those pair of integers. So for printing is easy. I just need to print the first and second of each edge. So we can do it first and then move to proofer code. But let's discuss together how we can write the function proofer to edges. So for proofer to edges, I know beforehand that the number of vertices in the tree is equal to the size of the proofer code plus 2. So now I know that the number of vertices is equal to the proofer code size plus 2. From that, I can calculate the degree because I know the degree, so I know the number of vertices and I can calculate the degree. So how can I do that? So I will loop over the proofer code, and I will see that I have 6, I have 3, I have 3, I have 0, I have 6, and I have 0. So I can know the number or the degree of each vertex. So we'll see that in the code. So I can calculate the degree, and then, as they have told us, I can find the leaves. So in order to find the leaves, I can use, as in the previous example, the priority queue, because in priority queue I can have those vertices with degree is equal to 1. Then I will loop over the proofer code. In the proofer code, I will pick the smallest leaf. So because if I have 0, 1, 2, 3, so I can know which one is missing. So I will pick the smallest leaf, I will remove it, and I will try to push in the edges both edges. So, and if its degree is equal to 1 of those vertices, I can repeat the same stuff. So let me start doing, and we'll try to understand what we will be doing in this proofer to edges code. So this is not that easy, but we will see a correct way to do that. So again, I have a proofer to edges code. So first I need to know the number of vertices. So int n is equal, so it's the proofer code, so this is the input because it's already read in the code. So I need to do that. So it's a proofer code dot size plus 2. This is easy. Then I need to calculate the degree. So I know that the degree, so it's a vector of integers, vector in degree. So I have n elements, and I would initialize all vertices to 1. The degree of each vertex is equal to 1. And then I will loop over each vertex in the proofer code. So, and if it's in the proofer code, so obviously it means that it has a degree. So it's if there's an edge that is associated with that vertex. So I can say degree of I plus plus. So if I have this one, it means that 6, it has an edge, because how can I retrieve the graph from the edge, from the vertex? So because it has an edge. So later on, 6 will be associated with an edge. So it has a degree 1. It has a degree 1. So it will contribute one more time. So if you can see, I have 6 here. I have it 2 times or 3 times, because 6, it contributes many times to other edges. 3 also, 0 also, and 6 also. So we have to take into account this. So at first I have each vertex, it should be connected because it's a tree, so it's not connected. So it has a degree equal to 1, and then each time a number appears here, it means it will have an additional edge in the tree. So as you can see, 0, it appears 2 more times. 6, it appears 2 more times because you have here 3. 3, it appears 1 more time, 2 more times. So as you can see, the other ones, the other edges, they are because they are bidirectional, so they appear both times. So this is a trick. So we have here the degree. Now that we have the degree, so we know that each vertex is degree, I can try to pick the leaves and then reconstitute the tree or the edges. So I'll be using priority queue of integers, and I will call it leaves. So in our case, let's pick those leaves and add them to the priority queue. So for int I equal to 0, I less than n, I plus plus. So if the degree of I is equal to 1, I will push into leaves dot push minus I. So it's the same as in the previous example, the previous exercise. So we'll reconstitute the graph in the opposite way. So and I will resolve the same problem using the algorithm that we have used in the PowerPoint. So now I need to loop over the Prüfer code. So for example, for int v Prüfer code, and I need to find or to associate vertex with that Prüfer code. So how can I do that? I will pick obviously the smallest vertex. So int leaf, so it's the same as in the previous one, leaves dot top, and I will do a pop. So now I have leaf, I will associate it with the first vertex. So what I will do that in the output, so the output is equal to edges, so it's a vector of integers, so I need to add both direction. So we know that we have either push back or we can use in place back, so it's the same. I will add minus leaf v, and a second time v minus leaf, because it should be in both directions. So I have added both. Next I need to check if, so I will decrement the degree of v. So I will do the same. If minus degree of v is equal to 1, I will push it into the priority queue. So at the end, I should not forget the last, as they told us to not forget the last vertex. So as you can see here, this is not the extended Prüfer code, so as if I have one extra vertex, so I need to pay attention for that extra one. So I need to add, so I need to place back the last one, so it's leaves.top minus leaves.top with the last one. So I know that the last vertex is equal to n minus 1, and also here is equal to n minus 1. So I can remove that if I want, but this is not important because the function has finished. So let me repeat. So we have used here a different approach in order to generate the edges. So it's the opposite way of how we have solved the previous exercise. So in a while I'll be solving the proof of the edges code like we have done in the PowerPoint. So here I have calculated the degree. So we know that each vertex it is connected, so it has at least a degree 1, and each time it appears in the Prüfer code, I will add a +1 to that degree. I have a priority queue because I need to sort the leaves in ascending order. I have pushed into this priority queue the leaves, and then for each vertex in the Prüfer code, I have picked the smallest one in the priority queue and formed the two edges, and then added that vertex v if it's in a leaf, and I have not forgot the last vertex because it should be extended and added to the edges. For printing, I just need to print the edges vector of pair of integers, so because it's a pair of integers. So but first I need to sort those edges. So I will say edges.begin and comma edges dot end, and then I will loop over the edges. So for example, pair of integers, pair int, so let's call it I, for example, edges, and I will print, so print f. So let me see the output. So I have just number dash a number, so percentage d dash percentage d backslash n. So the first one is I dot first, and the second one is I dot second. And this is it for the printing function. So let's see if we have some errors or if the output is correct. So I have here n edges, check, and so it's correct. So let me now erase and redo the Prüfer to generator code using the animation that we have done in our presentation. So instead of rewriting this code, so I'll be picking one of your friend's solutions, so and discuss it. So I will pick Saad Ali's solution. So let's see what he have done. So so let's see. So a Prüfer code. So I've just before exposing Ali's solution, so I have checked other solutions. They are correct, but they are very, in terms of complexity, they are very complex. They are doing a lot of nested loops, so this is not the correct way to do that because it will be very complex, even if it's correct, but this is not the correct way. So even though Ali, it has the least number of nested loops, but it's still okay. But I need to just show you the way he done it. So he just know that the number of vertices is equal to the Prüfer code size plus 2, and he has a vertex set. I don't know why the vertex set, because we have the answer. So okay, he needs to vertex set. So let's see. So he initialized the array of vertex set. So we know that we can do that directly. I just need to place, not use an integer. I can use a vector. It's more easier, and I can initialize the vector set directly. So I can write vertex set dot vertices comma 0, and I can do that just in one instruction. There's no need to loop vertices time. So then the number of occurrence of each vertex. So he so as I have done, he looped over vertices minus 2. So this is the Prüfer code, and he has incremented the number of occurrence plus 1. So he just counted the number of vertex as if it's giving them a number. So then they find the smallest label not present in the Prüfer. So he looped 2 times. So it could be done more easier. So there's a technique, because if you can sort those values, you can find just the first 2 numbers that they are not in the list, in the sorted list, but it's okay. So he looped 2 times. So for each element in the Prüfer code, he looped from 0 to the number of vertices, because he needs to find the missing value. So if the vertex j, the set vertex is equal to 0, so if it's not in the Prüfer code yet, so it means it's not in the Prüfer set. So he removes from Prüfer code and he prints the pair. So he makes the pair, and obviously he should add them into the priority queue, and then he decrements the Prüfer code number, because it should not be no more in the Prüfer code, or it should not contribute to the Prüfer or the trees generation. So for the last element, he repeated the same stuff. So obviously it's too much, because I have also a loop just to calculate the last one, and then he pushed all those values in priority queue into the edges. So he used the priority queue here, just not because he didn't want to sort the edges at the end. So it's a good way, but as you can see, it's very complex to do. So if I want to review other solutions from your colleagues, so they have done the same way. So I know that you have, some of you, they copied the solutions from each others. So let's see Fatma's solution. So Fatima, so she used a solution not similar to Ali, so let's see it. So she knows that the number of vertices is equal to the Prüfer code size plus 2. She used a degree, so all the degree at first they are equal to 1. She looped over 2 loops in order to calculate the degree, so this is too much. So as you can see, we can just loop once over the Prüfer code in order to calculate the degree. She pushed then, so it's similar to my solution. She pushed the degrees of the vertices whose degree is equal to 1. She looped v minus 2 times. She picked the smallest one, so she got the top. She popped. She decremented the degree. I don't know why she decremented t and code. I don't know. And then she have pushed both directions. And then if the degree of the Prüfer code is equal to 1, she pushed it also, and then repeated the same for the last edge. So it's similar to mine. With she can do some modification or amelioration to this code, so there's no need to for all these loops in order to calculate the degree. So I will end it here, and again, if you have any questions, do not hesitate to use the forum or to write to me. And again, thanks for watching and good luck.